Good day, everyone, and welcome to our webinar titled Potential Strategies for Integrating Solar Hydrogen Production and Concentrating Solar Power, a Systems Analysis. My name is Chris Worth, and I am the organizer for this meeting. We'll begin shortly, but first I have a few housekeeping items to tell you about. Today's webinar is being recorded, and the recording along with the slides will be posted to our website in about 10 days. We will send out an email to attendees once those are posted to the site. All attendees will be on mute throughout the webinar, so please submit your questions via the questions box that you should see on your webinar panel. We will cover those questions during the Q&A at the end of the presentation. With that, I would like to introduce our DOE host, Eric Miller, joining us from the Department of Energy headquarters in Washington, D.C. Eric is the Hydrogen Production and Delivery Program Manager in the Fuel Cell Technologies Office. Good afternoon, Eric.
Thanks, Chris. It's my pleasure today to introduce the speaker, Dr. Scott Papp, who is a principal member of the technical staff at the Sandia National Laboratories, working in Sandia's Systems Analysis Group. Scott received his BS in Chemical Engineering from the University of Wisconsin-Madison and his doctorate in Chemical Engineering from MIT. He has extensive experience in modeling and analysis of early-stage energy technologies based on cradle-to-grave economic and environmental metrics. In his recent portfolio, he has led techno-economic analysis projects looking at multiple biofuel production processes, a micro-concentrating photovoltaic electricity generating technology, and novel materials for air separation. We are fortunate to have him here today to present results from his recent Fuel Cell Technologies Office funded program that studied different technology pathways for hydrogen production from concentrated sunlight. And with that, I would like to hand it over to Scott.
Thank you very much for the introduction, Eric, and good morning or good afternoon to everyone listening, depending on where you're listening. I'm very excited to have the opportunity to speak in this forum, and I'd like to begin by thanking the Fuel Cell Technologies Office for their support for this work. This is a project that kicked off in late summer of 2014, and as you just heard, Sandia National Laboratories was asked to explore potential synergies between solar hydrogen production and concentrating solar power. I have a lot of material to cover, and I would like to leave room at the end for questions, so let's jump right in. Here's a basic outline of the topics I would like to cover today. I'm going to start by providing some background, including the context of the analysis, our goals, the general approach that was taken, and the main assumptions that were made. Then I'll provide a brief overview of concentrating solar power technology and draw a few very early conclusions on how it might be integrated with solar hydrogen production. I'll then take you through some results based on a set of analysis cases that we selected for analysis and finish up with some conclusions and insights. Okay, with that, let's begin with the introduction. Before we get into the details of the analysis, I wanted to take a moment to highlight where it fits into the broader energy landscape. On the perimeter of this schematic, we have energy sources such as wind energy, solar energy, nuclear energy, and chemical energy stored in biomass and fossil fuels. These energy sources can be converted into forms that are more useful to us, namely heat and electricity. So together with hydrogen, heat and electricity provide links between the various energy sources and a means for actually making use of them. The focus of the current analysis is on hydrogen and electricity production from solar energy in the form of heat. So we will be considering cases in which solar energy is collected and converted into heat, and that heat is subsequently converted into either electricity or chemical energy in hydrogen molecules. As you've already heard, our primary goal was to explore pathways for integrating concentrating solar power and solar hydrogen production. And the key question here is, do synergies exist that could reduce cost? The scope of the analysis was limited to process-level integration of concentrated solar power, which I'll refer to as CSP from here on out, and hydrogen production. So for example, we did not consider the use of hydrogen for energy storage at a CSP plant, and we also did not consider potential impacts beyond the plant gate, such as changes in hydrogen transportation costs. This was meant to be a preliminary look at integration of CSP and hydrogen production, and relied heavily on previously published analyses in those areas. On the CSP side, we used published reports and cost and performance models developed primarily at Sandia National Laboratories. These include power conversion calculations and reliability analyses, and capital and operating and maintenance cost estimates. Some of the key outputs of these analyses are estimates of the levelized cost of electricity from CSP, both for the current state of the technology and for future performance targets. On the hydrogen production side of things, we relied on DOE hydrogen production models, which present discounted cash flow analyses based on conversion efficiency and capital, O&M, and materials costs, with the primary output here being the cost of hydrogen per kilogram. And these are the DOE H2A models. In order to conduct our analysis, key relationships were extracted from these documents to construct a simplified Excel-based model of each potential scenario integrating CSP and hydrogen production. Our objectives were to identify important performance drivers and fundamental conditions that favor the integration of CSP and hydrogen production, and to understand the key uncertainties such that we could draw some robust conclusions. I just want to emphasize that our objective was not to conduct process optimization, as our modeling was conducted at a fairly high level. That being said, I will be showing cost estimates later in the presentation, but I would urge you not to focus on the absolute numbers, but rather try to notice the underlying trends and the conclusions that we can draw from them. Now is a good time to emphasize the fact that we did not make any judgments or assessments of the performance or cost of any components of either CSP or hydrogen production processes. All of the performance and cost estimates we took directly from the documents that I just mentioned on the previous slide. We simply combined these estimates to analyze potential costs for an integrated facility. So for hydrogen production, we use estimates from the DOE H2A models, and in particular the future central hydrogen production models, which feature startup years between 2025 and 2030. So again, in the future. For CSP, we used estimates taken directly from DOE and Sandia reports outlining DOE targets for CSP in 2020 under the Sunshot program. And note that for both hydrogen production and CSP, the assumptions are based on future systems projected out to high volumes where economies of scale have been achieved and cost reductions and performance improvements have been realized beyond the current state of the art. As we'll see, another important assumption that we'll need to make is regarding the price of electricity. According to the Energy Information Administration, current electricity prices in places with adequate solar resources are somewhere between 7 and 13 cents per kilowatt hour for retail industrial customers and 3 or 4 cents per kilowatt hour on the wholesale market. If we focus on solar energy in particular, a recent analysis from Lawrence Berkeley National Laboratory shows that solar photovoltaic power purchase agreements, or PPAs, have begun to reach grid parity after incentives are taken into account. If we look at this plot from the LBL report, the green circles are solar PV projects and the blue circles are CSP projects. And you'll see the most recent CSP project is highlighted there, the Ivanpah project. But as we discussed on the previous slide, we're interested in the price of electricity up to a decade or more in the future. And even though solar PV prices have come down substantially over the past few years, there are several factors that could lead to higher electricity prices going forward. One is potential increases in natural gas prices. With the retirement of many coal-fired plants, the share of natural gas in overall electricity generation has increased, and natural gas prices have historically been fairly volatile. So the stable prices offered by solar electricity technologies could potentially be attractive in this situation. Another factor is legislation that has been introduced to promote renewable and less carbon-intensive technologies, such as renewables portfolio standards, cap and trade programs, such as the one in California, and the US EPA's Clean Power Plan. All of these could increase the price at which renewable power is competitive. Finally, if we focus on CSP in particular, we note that this technology is unique in that it enables some amount of energy storage, which could command a premium compared to other renewable technologies like wind and solar PV. The point here is not to conduct a detailed analysis of the electricity prices. That's outside of our scope. The goal of this slide is simply to emphasize the fact that future electricity prices are highly uncertain. And because they are uncertain, we treated electricity price as a parameter in our analysis. So electricity prices enter into our analysis when we consider the electricity being sold by CSP plants and electricity being purchased by hydrogen production plants. We assumed for our analysis that hydrogen plants could purchase electricity at the same price for which CSP plants could sell electricity, just to simplify things. We also assumed that the CSP and hydrogen production facilities are owned by the same entity, just to do our calculations. Our analysis was conducted from the perspective of hydrogen production, so we accounted for the revenue from electricity sales in the calculation of the cost of producing hydrogen. So at a very high level, the hydrogen cost was calculated using the expression we're showing here. And as you can see, the electricity revenue is subtracted from total capital and O&M costs in the numerator here. Before we get into the actual analysis, I wanted to provide a brief overview of concentrated solar power. For those of you who may not be familiar with this technology, there are actually several different implementations of CSP that are being pursued, but we are focusing on power tower technology in alignment with the DOE Sunshot program. Basically, an array of heliostats, or mirrors with two-axis directional control, are used to reflect sunlight onto a solar receiver mounted on a tower. Inside the receiver, heat is absorbed by a working fluid or solid, as the case may be, and transferred to an electricity generation unit. The heat can also be stored for a number of hours if that's desirable. If we look at a typical breakdown of capital costs, we see that the majority of costs are for the collection and storage of heat from the sun, with electricity generation equipment accounting for a smaller fraction. The baseline CSP plant in our analysis is a power tower system with molten salt thermal storage and subcritical Rankine cycle electricity generation. In 2010, a Sandia National Laboratories analysis estimated that the levelized cost of electricity for such a system would be 15 cents per kilowatt hour, and the Sunshot target for this configuration is 6 cents per kilowatt hour in 2020. We divided the CSP plant into two major units for our analysis. The first is the system that collects light and converts it to thermal energy. This includes the heliostat field, the solar receiver, and thermal storage if it's present. The second unit is the system for generating electricity, including the steam generator, turbine, and cooling towers. You'll see schematic drawings like these throughout the presentation, so just keep in mind that the light to heat box here includes components shown in the schematic above. And as I just mentioned, the light to heat box represents the majority of CSP costs. So both CSP and solar hydrogen production use heat from the sun, and this heat can be treated as a feedstock in our analysis. The quality of this feedstock is determined by its temperature and also by its availability in terms of thermal storage, again, if it is present. The key point here is that the quality of the heat, as the quality of the heat increases, so does the cost. And this is important because, as we saw on the previous slides, the systems used to collect and store this heat are major costs for solar thermal technologies. The main reason that the cost of heat increases with temperature is that losses at the receiver become more significant with at higher temperature, and that's what's circled up here in the energy flow diagram. In addition, more exotic and expensive materials are required that can withstand the higher temperatures. So why would we want to go to higher temperatures? Well, at higher temperature, the generation of electricity and the production of hydrogen are both potentially more efficient. So a key trade-off that you'll see in this presentation is that between the efficiency of the collection of solar energy and the efficiency of the conversion of that energy to either electricity or chemical energy in hydrogen molecules. For the analysis conducted at Sandia in 2010 that I mentioned a few slides ago, they found that the optimal temperature for CSP is 565 degrees Celsius based on their assumptions. As I've said, our goal was to investigate opportunities for integrating hydrogen production and CSP processes in the H2A analyses that were used as the basis for hydrogen production processes. Electricity was purchased from the grid, whereas our analysis considers co-production of electricity from CSP. Our focus was on process level integration, as I've said. So the key question to ask for each process is, are there any potential synergies at the process level that would make co-location of CSP and hydrogen production attractive? One place to start would be to look for waste heat streams or byproducts from one process that could be fed to the other process. As we just saw, thermal energy is a major cost, so we focused on integrating heat streams between the two processes. With that in mind, taking a closer look at the electricity generation portion of a CSP process, we see that it yields a few byproducts that could potentially be used by another process. This is a very mature technology with extremely efficient internal heat integration. So waste heat exits the system at a fairly low temperature, roughly 40 to 60 degrees Celsius. And water is the working fluid in a closed cycle, so there are no significant material byproduct streams that could be utilized by another process. Essentially what this means for us is that we'll need to look to the hydrogen production processes for integration opportunities if we'd like to utilize waste streams as inputs. Okay, with that, we're ready to move to the actual scenarios that we explored for integrating CSP and hydrogen production. 3 scenarios were chosen based on 3 different hydrogen production technologies. The first was our baseline scenario, which featured CSP electricity coupled with polymer electrolyte membrane electrolysis at ambient temperature. Our second scenario was based on elevated temperature electrolysis integrated with a CSP plant. And our third scenario was based on high temperature metal oxide thermochemical hydrogen production integrated with a CSP plant. The hydrogen production technologies that form the basis of our 3 scenarios vary in terms of their maturity, as well as the amount of heat that they require as input. The variation in thermal energy input can be seen in the plot on this slide, which shows contributions to the overall hydrogen production costs from the collection of thermal energy as the blue portions of the bars. And the blue portion includes all capital and O&M costs associated with the heliostat field and solar receiver other than the cost of electricity. And other components of the hydrogen production cost are capital costs, indicated by the red portions of the bars, fixed operation and maintenance costs indicated by the green bars, electricity cost indicated by the purple bars, and materials cost indicated by the orange bars. All the data shown in the plot are taken directly from H2A models of hydrogen production And as I noted earlier, these are all future cases that assume technology maturation and high volume production that achieves economies of scale. PEM electrolysis is the bar on the left. This is a relatively mature technology that converts electricity into chemical energy in hydrogen molecules. Since the process takes place at ambient temperature, no heat input is necessary. High temperature electrolysis, the second bar, is similar to PEM electrolysis, but as the name implies, it's carried out at elevated temperature. As we can see from the size of the blue bar in that blue portion of that second bar here, this process uses a relatively small amount of heat to increase the efficiency of the electrolysis, but most of the energy input is still in the form of electricity. I should note here that the H2A data shown for high temperature electrolysis are based on thermal energy input from a nuclear reactor rather than solar energy. I'll bring this up again when we discuss the high temperature electrolysis scenario in greater detail in a few minutes. Thermochemical metal oxide cycles convert larger amounts of thermal energy directly to chemical energy, and you can see that reflected in the larger blue portion on the third bar here. You'll notice that there is still some electricity consumption that is required to drive process equipment. So with that brief overview of the three hydrogen production technologies, we're ready to move to our first scenario. You'll see that the variation in thermal energy inputs will be a major factor as we develop strategies for integrating these technologies with CSP. And at this point, I'd like to emphasize once again that our objective is to understand high-level trends and conditions that would favor integration of hydrogen production in CSP. I'm showing numbers here that were taken directly from H2A models, and we took those numbers at face value. I'll be showing more estimates of hydrogen production costs as we move through the presentation. But honestly, I hesitated to even include them because really these numbers aren't necessary to understand our key conclusions. So again, I'd urge you to resist the temptation to focus on the cost numbers and instead try to focus on the underlying behavior. Okay, with that said, let's begin with our baseline case, which is PEM electrolysis. Our PEM electrolysis case assumes no integration of hydrogen production and electricity generation, since, as we just discussed, PEM electrolysis requires no heat inputs. The main inputs to the process are water and electricity, and electricity is by far the largest cost. The capital costs are dominated by a handful of components, including the electrolyzer stack, the power electronics, and hydrogen gas management system. Here we see just how much electricity costs dominate the PEM electrolysis scenario. On the left, we see a plot that is similar to what we saw several slides ago. And in fact, the data that I showed then are the same as the fourth bar here, labeled Future Central. I apologize that the color scheme is different here. It's fairly obvious that PEM electrolysis requires low-cost electricity in order to be competitive. The plot on the right shows the current and future hydrogen cost based on H2A data for a range of electricity prices. I've also indicated the estimated costs at two different values of electricity price. First, an estimate of 15 cents per kilowatt hour came from the 2010 report published by Sandia, and 6 cents per kilowatt hour is the Sunshot target for CSP in 2020. It's clear that electricity prices on the high end of this plot will be problematic for PEM electrolysis. So PEM electrolysis was our baseline case, as I said, but there are really no obvious opportunities for directly integrating this technology with CSP. So let's now examine high temperature electrolysis, which does provide some of those opportunities. In the high temperature electrolysis process, a portion of the energy required for electrolysis can be supplied as heat, and this increases the overall efficiency of the hydrogen production process. The pie chart on this slide shows a breakdown of the cost of producing hydrogen from a published H2A case. However, as I noted several slides ago, this case was based on a supply of thermal energy from a nuclear reactor. A forthcoming H2A case that does not specify the source of thermal energy will be published soon with updated results. Again, the heat input for this process is relatively low. It requires 6.8 kilowatt hours thermal per kilogram of hydrogen versus an electricity input of 33.2 kilowatt hours per kilogram of hydrogen. And that is reflected in the pie chart as this large purple piece corresponds to electricity purchased from the grid. The H2A high temperature electrolysis case assumes nuclear-based thermal energy, as I just said, and it also assumes that electricity will be purchased from the grid. For our analysis, we assume that solar energy is utilized to provide both the heat and electricity needs of the process. So we assumed solar receivers with an output of 340 megawatts thermal would be used, and that's from the previous Sandia report that I referenced. This size power tower would supply a total amount of heat that is similar to the H2A case based on nuclear power. And the solid particle receivers in these towers would be able to provide heat at roughly 850 degrees Celsius, which is similar to the temperatures that would be available from a nuclear reactor. Two key factors to keep in mind as we explore integration options are that electricity's consumption is high, and also that the process yields low temperature waste heat that is not particularly valuable for other processes. So how can we integrate this technology with CSP? One option, which we call case one, would be to construct a single tower dedicated to providing thermal energy and multiple additional CSP towers to provide electricity. In this case, 11 additional CSP towers would be necessary to supply electricity, for each tower supplying exclusively heat for hydrogen production. And there's no process level integration of hydrogen production and CSP. The only interaction between these two processes in this case is the transfer of electricity from the CSP plant to the hydrogen production facility. So really there's no reason that the towers need to be co-located as long as they are connected by the grid. You'll notice that case one looks very similar to the H2A case, except that here we have both heat and electricity being provided by solar energy. Another option for integrating high temperature electrolysis and CSP is shown here. Case 2 features a single tower operated at 850 degrees Celsius, with some of the heat being sent to the hydrogen production facility and the remainder being used for electricity generation. All thermal energy is used to produce hydrogen, so the allocation of heat to hydrogen production and electricity generation is balanced so that no excess electricity is generated. For case 2, 9% of the total thermal energy is used directly to raise the temperature of hydrogen production, and 91% of the thermal energy is used for electricity generation, resulting in a total hydrogen production of roughly 80,000 kilograms per day. Thermal energy for electricity generation is at a higher temperature than would normally be expected for a CSP process, so electricity generation efficiency would be higher. However, the cost of collecting that thermal energy is also higher, as we discussed previously. And this is the key trade-off that we identified earlier in the presentation. Here we show the breakdown of hydrogen production costs for case 1 and case 2, and you'll notice that instead of the purple bars that we saw before indicating electricity costs, now we see pink bars indicating capital costs for electricity generation, and light blue bars indicating costs for thermal energy for electricity generation. Case 1 is a less expensive option due to economies of scale and lower costs for thermal energy collection. The increased power generation efficiency in case 2 is not sufficient to make up for the higher cost for thermal energy collection. We can compare the results from case 1 to the case in which electricity is purchased from the grid in the plot at right. Instead of a stacked bar chart, we have a stacked area plot with electricity price as a parameter on the x-axis. The large purple wedge is the cost of electricity, and the hydrogen cost in case 1 is indicated by the red dashed line. Since we said earlier that electricity is the main cost driver for the H2A case, it's not surprising that we see a large swing based on electricity price. In general, the cost of CSP versus grid electricity will determine whether integration of CSP with hydrogen production is viable. And if we look at the plot, it appears that case 1 would be attractive if electricity prices are above about 9 cents per kilowatt hour. Here I'll also refer back to my earlier comments regarding electricity prices. So even if CSP is more expensive than grid electricity at any given point in time, the ability to lock in CSP prices over long periods of time may be attractive if someone's making a long-term investment in a hydrogen production facility. We also looked at one other high-temperature electrolysis case in addition to case 1 and case 2. In case 3, we utilized 2 towers for hydrogen production, each providing thermal energy at a different temperature. So 18% of the thermal energy collected at 850 degrees C is used to raise the temperature of the electrolysis, and the remainder is combined with thermal energy from a second tower collected at a lower temperature to generate electricity. In this configuration, solar and thermal energy is collected at a lower temperature in the second tower, which is less expensive, but at the same time, electricity generation is carried out at a higher temperature than our baseline CSP plant, which increases the efficiency from 42% to 48%. Before we get to the results for case 3, I wanted to take a minute to highlight the fact that combining heat from multiple towers does have precedent in industry. Specifically, eSolar has taken a modular approach to CSP in which their total plant output is deployed in 12 megawatt thermal or 50 megawatt thermal increments. So a similar approach could be taken in collecting heat from multiple towers, producing hydrogen and electricity, as we do in case 3. Okay, so here we see the results from all 3 of our high temperature hydrolysis cases, and one conclusion that we can draw is that the operation of multiple towers at 2 different temperatures reduces hydrogen cost. Case 1 with the 12 large towers remains the lowest cost option due to economies of scale and cost-effective collection of thermal energy at temperatures that are optimized for both hydrogen production and electricity generation. Case 3 reduces cost versus case 2 due to increases in efficiency of thermal energy collection and conversion to electricity, but it still doesn't match the cost of case 1. That being said, there may be some optimum configurations somewhere between case 1 and case 3. In reality, one could vary the number and sizes of both high and low temperature towers at a given site, and that optimization would lead to the lowest possible hydrogen cost. Here we selected 3 representative cases to illustrate the key factors that we need to consider. So without conducting such an optimization, it's difficult to say whether there is any potential advantage to co-locating CSP in high temperature electrolysis processes. Now let's move on to our final scenario, which is integration of metal oxide thermochemical hydrogen production with CSP. First, one slide overview of metal oxide thermochemical cycles. Essentially, these cycles convert thermal energy directly to chemical energy in hydrogen molecules. The process is based on metal oxide particles that are moved between 2 reaction chambers at 2 different temperatures. On the top of the diagram, we have the reduction chamber. Here, solar thermal energy is used to drive the reduction of metal oxide particles at high temperature, resulting in the generation of oxygen. The reduced particles are then sent to the lower chamber, where the particles are reoxidized in the presence of steam to form hydrogen. The hydrogen production reaction occurs at a lower temperature than the reduction reaction, so thermal energy is rejected at a relatively high temperature as particles exit the reduction chamber. Although there is heat recovery between the particles flowing in opposite directions, inevitably there will be losses that result in quote-unquote waste heat. And that waste heat will be the focus of our strategies to integrate with CSP. So our analysis was based on H2A assumptions, and I've listed some of the important ones here. Reduction of metal oxide particles is carried out at 1500 degrees Celsius, and the hydrogen production reaction is carried out at 1150 degrees Celsius. The metal oxide particles are Ceria, and the metal oxide cycles are actually carried out in 231 small 4 megawatt thermal towers, rather than a single large tower as you'd see for CSP. And these numbers come from an optimization that was done previously at Sandia. As I mentioned earlier, this H2A model is based on Sandia data, and that has not been published, although you can find some information in the Fuel Cell Technology Office's annual merit review documents and annual reports. Although I said that the waste heat from the metal oxide cycles will be the focus of our integration strategies, our first case does not utilize this waste heat. This is similar to the H2A case, in which process electricity is purchased from the grid. So here we see a breakdown of the cost from the H2A model, and we see that electricity is a relatively minor cost. It's mainly required to run compressors and other equipment in the hydrogen production plant, and also to move heliostats. The main costs are related to the collection of thermal energy, as you can see here. In our second metal oxide case, the waste heat from the process is used to generate power for internal use. So we have extra capital costs for the electricity generation equipment, but no electricity costs, since electricity generation is sufficient to meet process power needs with a small excess perhaps that can be sold to the grid. So in essence, this is both a solar hydrogen production plant and a CSP plant. However, because the power generation system is smaller, it doesn't enjoy the economies of scale and high efficiency of the full-scale CSP. Here we see results for case 1 and case 2, again with electricity price on the x-axis. For case 1, the hydrogen production cost increases as electricity price increases, and for case 2, the opposite is true, since electricity revenue increases. It's difficult to see the total hydrogen production cost from the bottom plot, since this purple section is electricity revenue that should be subtracted from the other costs. So I plotted the total hydrogen cost for both cases on the plot to the right. You can see that the electricity generation from waste heat in case 2 reduces hydrogen cost if the electricity price is greater than about 7 cents per kilowatt hour. But electricity is a relatively minor cost for this process, so you don't see significant benefits until the price reaches about 10 cents per kilowatt hour. We also investigated one other option, case 3, which integrates the metal oxide cycle with a traditional CSP plant. In this case, the excess thermal energy from the metal oxide cycle is combined with the thermal energy from a typical CSP tower. So in an optimized CSP plant, solar thermal energy is collected at a lower temperature than the 1500 degrees that we're considering for metal oxide cycles, and that leads to lower costs for collecting that heat. However, since the high temperature waste heat from the metal oxide cycle is combined with the heat from the low temperature CSP tower, the temperature of electricity generation is increased, and that leads to an increase in efficiency from 42 to 48%. So not only are we utilizing heat that would normally be wasted, that heat is being used to increase the efficiency of the entire electricity generation process. So by doing so, we're essentially amplifying the value of that waste heat. Here I'm showing the same plots that you saw 2 slides ago, comparing case 1 and case 2. Now I'm going to change the scales on these plots and animate in a third plot showing the results for case 3. So as you can see, the case in which a metal oxide thermochemical cycle is integrated with CSP has significantly higher capital costs for electricity generation, and that's represented by the salmon color, and an extra cost for the collection of thermal energy at a lower temperature, and that's represented by the light blue. This is due to the fact that we're effectively extending our system boundary to include the CSP plant. However, these costs are more than offset by an increase in electricity revenue, represented by the light purple color. So the blue line in the plot on the lower right represents the overall hydrogen cost for case 3, and we see that this case is strongly dependent on our assumptions regarding electricity price. If the price of electricity is above approximately 8 cents per kilowatt hour, in our set of assumptions, case 3 starts to look quite attractive. But once again, I'd like to emphasize the fact that we're interested in trends and insights rather than specific numbers. Even if you don't believe that the capital costs for hydrogen production represented by the red color are correct, the general trend remains the same. This will just shift the blue line up or down. Now, the results that I've shown thus far for the integration of CSP with metal oxide thermochemical cycles are based on an optimal hydrogen production cycle with very efficient heat recovery and a thermal reduction temperature of 1150 degrees Celsius. This leads to high hydrogen production efficiency and relatively little waste heat. In reality, several advances in the technology will be necessary to achieve this level of performance in the hydrogen cycle. So we also examined a case that we would be more likely to see in the nearer term. This second case features a lower hydrogen production temperature of 800 degrees Celsius and less efficient heat recovery between the metal oxide particles. And this results in more waste heat and a lower hydrogen production efficiency. If you recall, in our first metal oxide thermochemical cycle case, no electricity is generated within the process. If we compare the results for an optimal case and a less efficient process with more waste heat, we're not surprised to see that the optimal case results in a lower hydrogen production cost. That's what we would expect to happen. However, in our other cases, waste heat is utilized to generate electricity within the process, and this makes the less efficient process look more attractive. Although the less efficient hydrogen process has higher capital cost and larger thermal energy input for a fixed hydrogen production quantity, this is offset by an increase in electricity revenue. If we look at overall hydrogen production cost, we see that the less efficient hydrogen process, denoted by the dashed lines in the plot, actually results in lower hydrogen costs for most values of electricity price for both case 2 and case 3. Thus, we see that the potential synergies do exist between CSP and metal oxide thermochemical cycles, and further, these synergies look particularly attractive at earlier stages of the hydrogen technology development, that is, for processes that have more so-called waste heat. And so this excess heat should be viewed as a potentially valuable byproduct of the hydrogen production process that would definitely have value for a CSP process that was co-located. So the previous slide contained the last set of results that I will present today. Before I move to questions, I'd like to end with the key conclusions and insights that I hope you'll take away from today's presentation. But before I get to those, I'd like to reiterate my previous statements about the uncertainty and sensitivity of the results that I've shown today. The solar hydrogen technologies that I've discussed today are obviously at an early stage of development, and the cost and performance of these technologies 10 or 15 years in the future are highly uncertain, to put it mildly. At this point in time, detailed process optimizations are frankly premature. That being said, I did present cost numbers today, but in my view, again, those are not the results of our study. The real results of the analysis are the set of insights regarding potentially favorable conditions for the integration of CSP and solar hydrogen production. And I do believe that these results are robust. They are driven by the inherent characteristics of the processes, and they are unaffected to a large degree by the uncertainties in the absolute hydrogen production costs. Okay, so let's begin with a few general conclusions. These may not seem extremely insightful, but I believe they are worth mentioning since they will drive the more specific conclusions that I'll discuss in a few moments. So first, we saw that the collection of solar thermal energy is a significant cost for both CSP and solar hydrogen production. The efficient collection and use of this energy will be crucial in order to make these technologies competitive, and thus heat integration is a potentially attractive strategy for improving the performance of both CSP and hydrogen production. Any heat integration strategies must account for the fact that the optimal temperature of a CSP process is lower than that for hydrogen production. If we pursue heat integration between CSP and hydrogen production, we soon realize that CSP does not yield significant waste heat or materials byproducts, so we'll need to look to the hydrogen production processes for potential heat flows. And finally, we saw that electricity prices have a significant impact on our results. Our study was conducted from the perspective of hydrogen production, and in this case, integration with CSP is favored when electricity prices are high, and especially if they are higher than the CSP price. Before I move on to conclusions related to specific technologies, you'll recall that we did briefly touch on hydrogen production via PEM electrolysis, but there really is no significant potential for integration with CSP since there is no input of thermal energy required. And there are no waste streams of potential value for CSP. So the connection is solely through electricity prices since the economics of PEM electrolysis are driven by the price of electricity to a large extent. Okay, focusing on high temperature electrolysis, we saw that this process is characterized by a relatively small input of thermal energy compared to its electricity needs. So most of the solar thermal energy collected in an integrated process will be used for the production of electricity, and that's an important point. Because only a small fraction of the total thermal energy is collected at the higher temperature for the hydrogen production process, the optimal configuration will likely feature multiple towers at different temperatures. And this would lead to more efficient collection and conversion of thermal energy. The exact number of towers and extent of heat integration would need to be optimized on a case-by-case basis. It's possible to have essentially separate CSP and hydrogen production facilities in which only electricity is passed between the processes. And it's also possible to divert some high temperature heat from the hydrogen production process to raise the efficiency of electricity production in the CSP plant. And again, this will be driven by local conditions to a large extent. For metal oxide thermochemical cycles, unlike high temperature hydrolysis, the electricity demand of the process is relatively small, and in fact the amount of high quality waste heat from the process is likely to be more than enough to supply all the internal process heat and power needs. However, if we consider a standalone hydrogen production process with no integration with CSP, because the electricity demand is relatively low, whether or not the waste heat is used to generate process electricity or the electricity is purchased from the grid has only a small impact on hydrogen production costs unless grid electricity is expensive. If we consider hydrogen production processes integrated with CSP, there are potential synergies that may be attractive. The waste heat from hydrogen production could then be used to increase the efficiency of the entire electricity generation step by roughly 15% on a relative basis. And this essentially amplifies its value. So in simple terms, we can view the waste heat from the hydrogen cycle as a byproduct that would be potentially very valuable to a co-located CSP plant. Finally, we revisited some of our assumptions regarding the thermochemical hydrogen production cycles. And we might expect that in the near term, metal oxide cycles would generate significantly more high-quality waste heat than would be available for use in a CSP plant. And this can be viewed as a potential revenue stream as the technology continues to develop, so perhaps a bridge to the future. So that concludes my presentation. Before we go to questions, I'd like to acknowledge Tony McDaniel and Ivan Ermanowski at Sandia for lending their considerable expertise in the area of metal oxide thermochemical hydrogen production. Tony and Ivan are also on the panel today to help me field any technical questions related to that process. I'd also like to acknowledge Cliff Ho at Sandia for being a resource on the CSP side. And I'd like to, of course, acknowledge Eric Miller and Katie Randolph and the Fuel Cell Technologies Office for their support of this study. So although I wanted to acknowledge everyone who made this study possible, my acknowledgement should not be taken as an endorsement of my conclusions by anyone that I've mentioned. And of course, any errors in this presentation are mine and mine alone. So with that being said, I'd be happy to answer any questions. Thank you very much for your attention.
Great. Thanks, Scott. Thanks very much for a very good presentation. And I just wanted to do a sound check. As Scott has mentioned, we've got both Tony McDaniel and Ivan Ermanowski standing by as additional distinguished scientists to help us in the Q&A. Could I get a quick sound check that you're with us, Tony and Ivan?
Yes, Eric, this is Tony McDaniel from Sandia campus in Livermore.
Very
Sound
good.
check.
All right, Ivan.
Ivan Ermanowski, Sandia, New Mexico.
Very good. We've got several very good questions from the audience. We'll get to as many as we can in the next 10 minutes. Then we'll try to field the rest offline if possible. Since we've got the panel on, this is probably one you guys can handle relatively quickly. One of our questions is it possible for the CSP towers to reach the temperatures required for metal oxide thermochemical cycles?
Should I take that?
Yeah, Ivan.
It's yours.
The short answer is yes. CSP towers right now are designed for different temperatures, namely what the limit is of molten salts, maybe 600 Celsius or so. But in our work, we have looked extensively at field designs, and the short answer is yes. We're looking at concentrations of about 3,000 suns, and we think we can absolutely reach them in smaller fields. So we're not talking hundreds of megawatts, but maybe a couple of tens of megawatts.
Okay. Thanks, Ivan. Scott, I've got a specific question on a specific slide. There's a question on slide 20. Maybe you could go to that. On slide 20, what is the size of the plants analyzed in terms of kilograms per day hydrogen produced? Also, as electricity usage for hydrogen production decreases across cases, what happens to the electricity not used for hydrogen? For example, the delta in electricity between low temperature PEM and thermochemical cycles.
Okay, on slide 20. I would have to get back to the questioner on this. These were taken directly from the H2A cases, so they are available on the DOE website. But I don't recall what the assumptions were for these particular H2A cases. And in terms of the question about the electricity, if I understand it correctly, so these processes all are purchasing electricity from the grid. So they are purchasing just enough to run their processes, and none are being generated by these processes. Did I understand that question correctly?
I think you're right, and I think that if I'm correct, that all of these cases were based on central production models.
Right.
So we can come up with it. We have a range of what they were, but we can dig up those cases pretty quickly and probably come up with the kilograms per day for each of these.
Right, and if I recall, they were on the order of 100,000 kilograms per day. If that sounds right to you, Eric.
So yeah, they may be different in the three cases, but they're all the same order of magnitude. We can get that in a few minutes. We'll dig that up. Let me ask a couple of other questions that have been posed. We have a question about alkaline versus PEM electrolysis. Was the alkaline electrolysis considered as well? And that also comes to the H2A cases. I may be able to help you with that if you don't have an answer.
Yes, we did not specifically look at that, so I will definitely look to you, Eric, for any additional input you can provide.
Right. I will say that the cases that have been shown in this study were based on a most recent PEM electrolysis case study that was very well vetted by technology stakeholders. What I will also say is that the previous case study that had been published by DOE was more of a based on alkaline electrolysis. There was some differences in the results, but it was more of a preliminary model. And I think the key difference was that alkaline electrolysis is a more mature technology, so they have achieved some of the economies of scales that are not yet reflected in the bars that you're showing for PEM electrolysis. Although there's not a huge difference in terms of the cost, they're still dominated by electricity cost. That's maybe the longer than short answer, but it's a start. Okay, I want to get back to some more questions that we have from the audience. This is actually quite thought-provoking, and I think everyone might have had the same question as they saw slide 41, and I think you did describe it, but I would give you a chance to do it again. How can the cost of hydrogen go to zero on slide 41?
So if the cost of hydrogen goes to zero on slide 41 because of the way we set up our economic analysis. So as I said, we drew our boundaries to include both the hydrogen production side as well as the CSP side, but we are looking at this from the perspective of hydrogen production. So all of the electricity that is generated that is sold to the grid, and that revenue is treated as a negative cost in our analysis. So it's simply a matter of how we set up our analysis since we were hydrogen focused. And so again, the electricity is sold to the grid, that is the revenue, that becomes a negative cost, and that's where that comes from.
Thanks, and that shows up on several other slides of the scenarios.
Yes,
and it's all about relative directions as opposed to absolute cost, as you've answered.
Exactly. You could look at it in a different way. You could look at it and say the process is producing waste heat, and that can be that heat can be sold to an adjacent CSP plant, and that CSP plant could be considered a separate entity that would purchase that heat. So it's just the way that we drew our boundaries and the way we set up our analysis, really, that generates this result.
Great, thanks. And let me get a few more questions in the last few minutes here. Has any research been done on PV-generated excess or non-peak electricity as input for electrolysis and fuel cell storage?
That is definitely outside of the scope that we considered. We did not consider specifically, we considered specifically outside of our scope any sort of storage of electricity. So we did consider storage of heat, the thermal energy in the CSP side, but really we drew our boundaries around these two processes and didn't consider any electricity storage.
Okay, so that could be mentioned. Is that Tony? Do you have a
yeah,
comment?
I just had a quick comment about that. I think the way that you, Scott, have parameterized the electricity cost, you could essentially capture some of that information, right? Because I think that maybe I'm interpreting the question a little incorrectly, but I think the real driver is, because the process is so sensitive to the electricity cost, if you can conceive of any notion that involves PV and storage and whatnot that would drive your electricity costs down versus up, the impact is still representative effectively here because you parameterize the electricity cost anyway.
Okay.
That's true. You could see the impact there.
Right.
Yeah. I want to get it out, but it's there.
Okay, Tony, I want to get to a couple of questions related specifically, I think, to the thermochemical cycles. And I think, in your opinion, one question goes, how far away are we from commercially viable systems and at what scale?
So I guess I can take that one. Let's see. We are at a fairly low technology readiness level now. If we go by, I think the way DOE anticipates us making progress in the future and all of our kind of future case studies, within a few decades, I believe that this technology would be commercially viable. That's what we kind of strive for, developing the technology at kind of that rate.
And what scale do you envision?
Well, we're targeting these large-scale centralized facilities, and so we're talking about plants, and many of them, each of them making 100,000 kilograms of hydrogen per day. And those are our goals.
Okay. And a follow-on question maybe for all three of you. If you had to prioritize the R&D needs, so what would they be?
Okay, so a lot of the analysis that we've conducted so far, they rely on a lot of these assumptions about, what is the ultimate kind of, what can we ultimately achieve with this technology? And there are many R&D needs in there. And if you had to prioritize them, at least in the CSP hydrogen community, it's definitely materials for these redox active cycles, specifically for our two-step thermochemical cycle, as well as reactor technology to achieve these really high temperatures and efficiencies from this process that takes concentrated solar energy and converts it directly to hydrogen. So it's definitely, our needs are aligned along materials and reactor design technologies.
Okay, great. Any other inputs from either Yvonne or Scott on that topic? So we're running to an end of our webinar, and I want to give you a chance to chime in.
I don't think I have anything to add. That's basically it. We're still learning how to properly account for everything in these reactor models, and how to optimize for hydrogen production, and of course putting that into practice. And on the materials side, I think there was a question earlier. These are high temperatures, and we're looking to lower that to something that we consider thermodynamically optimal based on our models, maybe 1350 Celsius or something like that.
Very good. And Scott, do you have any final comments before we hand it back over to Chris for the final cleanup?
Just one thing that I think that came up during my analysis that is probably outside of what Yvonne and Tony normally think about is the heat exchange between the two processes. That's an area related to your specific question that would need further development for this particular case that we looked at.
Very good. And I think with that, our time is up. I think it's time to hand over to Chris for final words.
Thank you, Eric, our presenter Scott, and our panelists. Very great presentation. If you would, Scott, go to the very last slide there, and thank you slide towards the end. Excellent. Everyone, that concludes our webinar today. If we didn't get to your question, please feel free to email the presenter directly, and they will try to respond in a timely manner. Again, I'd like to thank everyone for joining in and remind you that the webinar and slides will be available online at the Fuel Cell Webinars website shown in about 10 days. That's the first website link you see there on the slide. Also, I encourage everyone to sign up for our monthly newsletter, which will include upcoming webinars. You can sign up for that on the second website shown below. Have a great week, everyone. Goodbye.